I would like to start by acknowledging that this is joint work with Fan Wan from the University of Warwick, Dr. Wan Chan, who graduated from CMU in statistics, Professor Yi Yu at the University of Warwick, and Professor Alessandro Rinaldo at UT Austin. So for the talk today, I will focus on models related to network data. The applications of network data are very common these days. They range a wide domain of settings. This includes applications with neurological data where the networks can represent different regions of the brain and how they relate to each other over time when a person or an animal is performing a task. Networks can also be used to represent social interactions between people who are part of a social network and how their interactions evolve over time. Let me talk about the model, and then I will give very specific examples of this model. So the data that we have consists of a multi-layer network G. The network G has four things: a set of nodes V1, a set of nodes V2, and a set of edges E and layers L. The set of nodes could be things like countries and different products that the countries produce, or they could be people who are part of a social network, or they could be the different regions of the brain. Those would be the nodes. And then the edges, they represent interactions between node I and J at layer L. So for example, node I and J could be connected in one layer. Maybe they are connected in TikTok, but they might not be connected on Instagram. That Instagram would be the other layer. And so the edges are represented by triples like this. And based on the network, we can construct the adjacency matrix, which represents a tensor. In this case, it's a tensor adjacency object that indicates with value 1, if I and J are connected in the L layer, then we put Aij equals to 1. Otherwise, we put that value to be 0. The framework is very general, that the nodes don't even have to be equal, but for this talk, I will take them to be the same. An example of nodes being different is in economics, where the nodes can be countries, and then on the other side, you can have nodes that are different products that countries produce. So this is the data. The data is a three-way tensor. And here are some examples of this kind of data. So in this one, we have different networks. One network corresponds to each layer, and the layers represent airlines. So Lufthansa is one layer, and Lufthansa has a network where the nodes are airports, and we put an H between them when there is a flight between those two airports via Lufthansa. Then we also have Air France. Air France has its own network, right? If two airports have a flight between each other via Air France, then we put an H. Similarly, we can have multi-layer networks between people. Even if you have a group of people, you could have edges that represent whether or not two people are friends. So we could have a friendship network. But we could also have another network that captures some negative interaction that people have. Or a network that represents job relationships. For example, if two people work in the same place, maybe we put an edge. So that would be a different layer related to job. So different types of things can represent different ways that people connect. In biology, for example, I'm working on an extension of this work to an applied setting. The layers would be different types of fMRI that people get. So you have a person that goes to an fMRI, and the first time they are just there and they rest. That is the first layer, and you collect a network based on the regions of the brain. In the second type, you go there, but this time you might perform a task like looking at a picture or answering questions. That would be a different layer, but you would have the same set of nodes, which would be different regions of the brain. So those are types of data that can be represented by multi-layer networks. And that is the object of study in this talk. I should start by saying that, but by giving some notation. Unfortunately, because these are three-way tensor data, the notation can be a little bit overwhelming, but it's not difficult if we keep the big picture in mind. So for a tensor M, we have P1, P2, and P3, the different dimensions. There is something called the matrization of the tensor along each dimension, S. And basically, what that means is you have this three-way object, and you just fold it into a matrix. And if S is 1, you put the number of rows as the first dimension, and then the other two dimensions, they correspond to the columns. This is similar to what we do when we take a matrix and we just make it a vector, right? It's the similar operation, but now for tensors. So we can mathematically define that. Also, for a tensor M that has dimensions P1, P2, and P3, there are these objects called the token ranks. And the token ranks, they are the ranks of the tensor when we do the matrization along the different dimensions. And each dimension produces a different matrix, and then you take the rank of that matrix, and you get three numbers that are the token ranks. Unlike the matrix case, if you have a matrix, the rank by rows and the rank by columns is the same. But for tensor, that is not true. So the ranks are three different numbers. But we will assume typically that these numbers are small for the kind of structure that we want to estimate. Another operation that we can perform with tensors is tensor multiplication by a matrix. Remember that in linear algebra, we have a matrix A times a vector, but now we have a tensor M times a matrix. It is the equivalent operation, and basically the operation, I guess I switched this. Basically, the operation is just the equivalent. You multiply the tensor with the matrix along one dimension. And that is just the similar operation to multiplying a matrix with a vector. And we can do this via across the different dimensions that the tensor has. Okay, so now that I presented that, let me talk about the probability model that we are going to put on the object A, which is our data. So our data is like this. Number of nodes, but number of layers, that is the dimension of this tensor. So let's see what assumption we are going to make about the entries of this object, the tensor that we are going to model. So for this, what we're going to do is that we're going to assume that there exists a sequence of weight matrices W and a sequence of latent positions xi. So basically, every node I is going to have a latent position. In the case of the brain example, the nodes are different regions of the brain that you can create. Typically, you would create like 300, 400 regions. And each region would have a latent representation, which would be a vector in some dimension RD. And then we also have these matrices WL. For each layer L, we have a matrix WL. And these matrices are going to be used in modeling the likelihood. So the likelihood of the data is going to be the product across layers, and then the product across pairs of nodes. And then for each entry, AIJL, we're just going to have a Bernoulli, right, with probability of success, PIJ. So it's going to be Bernoulli, PIJL. And that Bernoulli, the probability of success is going to be written like this. The product between the latent vector for I times the matrix WL times the vector for the node J. Okay, and that's just the likelihood. So basically, conditioning on the latent positions X, the entries of the tensor are going to be assumed to be independent. And we run this model as multi-layer random dot product graph with fixed latent positions. By fixed, I mean that the xi's are assumed to be deterministic, although unknown. Okay? This model, in the case where L equals 1, so we only have one network, this model is just the usual random dot product graph model, and that model itself is a generalization of the stochastic block model for networks. So this is like multiple generalizations. We go higher than SVM, and then we consider more layers for the data. And so in summary, AIJL is a Bernoulli with probability of success that depends on the node I, the node J, and the layer L. That would be the model for our data. Okay, so Here, I need to introduce some notation. So for a positive integer D and L, D is going to represent the dimension of the latent positions, and L is the number of layers. For that, we're going to say that F and F tilde are two distributions with support in X and X tilde subsets of RD. And we are just going to require that, and we're going to say that they are a random inner product distribution if this is true. When we generate X from F and X tilde from F tilde, and we multiply by the weight matrix, this number is between 0 and 1. This is just because these Bernoulli numbers that we have here, these probabilities, they need to be between 0 and 1. So if we're going to impose a distribution on this and on this, then the product better be in 0, 1, so it is well defined. An alternative way would be not to have that constraint and then use something like logistic lin or some other kind of link function. But the theory and the methods are cleaner if we don't use link function. Okay, so now let me describe the random position model for the tensor. So this is called the multilayer random dot product graph with random latent position. Essentially, we have the same likelihood as before, conditioning on the latent positions, but instead of assuming that the latent positions are deterministic, now we're going to assume that they are random. And those random latent positions, xi, one for each node, they are drawn from the distribution f. So there is a distribution x where the latent positions are drawn from. They are independently generated from f. Conditioning on them, we have the same likelihood as before, and we write the model like this: multilayer random dot product graph with distribution f for the latent positions and weight matrices for each layer. So one thing about this is, yes, go ahead.
So when it seems like the weight matrix is for every layer, right?
Every layer has some different matrix.
Between layer weights.
Pardon?
What about the weights between there? Because the weight is basically the probability of one is connected to the other one.
So the probability that one is connected to the other is this. So the probability that I and J are connected in layer L, the probability that I and J are connected in layer L, this is Xi transpose WL Xj. This is the probability that they are connected.
I'm saying, like, what's the probability of, like, cross layer? Because you.
Oh, so we don't have cross layer edges. That's a great question. So in multi-layer networks, you could also have a cross layer edges. There is some, but we don't have that here. So here in this type of data, we are assuming that we have a network on the nodes, and then there are different networks. But in some applications, actually, you could also have layers, edges across layers. So that would be something that we didn't explore in this work. But that's a great question, actually. Yeah. In some biological networks, actually, it makes sense to have across layer edges. So we did not include that, but that is a very good question. Okay, and so what is the difference then between random and latent position? So if the positions are fixed, that means that the entries of the tensor are independent because the positions are fixed and they are generated from independent parameters from a Bernoulli. If the positions are random, though, if you think of this as a Bayesian hierarchical model, you have a distribution F. You create a latent position. Then you create the data. Then now the data in the matrix A, they are not independent if we allow for random positions. Okay, so that's one distinction between the two models. Why it's necessary to have two different models will be more evident when I talk about dynamic tensors in a moment. Okay, so there is a notation here that I will not go into, but basically, this model can be written in a concise form. So the tensor P that has the probabilities of links, that can be written in tensor notation in terms of X, a matrix Q, where the matrix Q has all the weight matrices inside, and then some matrix S. So this is not so important, but we can do it and write the model in a cleaner notation. Okay, so here I want to give more intuition about this model. So in this example, the number of layers is 2, and the dimension is 3. And suppose that the weight matrix for layer 1 looks like this. the weight matrix for layer 2 looks like this. Then, if I want to look at the following, if I look at what is the probability that node 1 and node 2 are connected in the first layer, what is this probability versus what is the probability that node 1, node 2 are connected in the second layer? The probability of the first one would be this inner product. The latent position for node 1, the latent position for node 2 are in between the weight matrix for the layer 1. For the second probability that I wrote down here, that would be the same, but replacing the second weight matrix instead of the first weight matrix. But if I expand this, it looks like this. And you can see that in this expansion, this coordinate, the tier coordinate of the latent positions, the tier coordinate is affects the probability in the same way. So that means that the tier coordinate has the same effect across probability, across layers. However, the first and second coordinates do not have the same effect across layers. So there is some layer dependent things, and that will be the first coordinate and the second coordinates. And there are some latent things that are the same across layers. So this model allows us to have something that can model the probability of success in a way that there is information shared across layers, but there is also individual information within each layer. So that is why we want to have this weight matrix in between. Otherwise, the model would not have that feature. We would not be incorporating information from layers and then layer-dependent information, and also information that doesn't depend on layers. So I hope that clarifies why we need the weight matrix. In fact, people have been using this recently in applications of the brain, like I was saying, when people are performing different tasks. And in those examples, it makes sense to have information sharing across layers, because you would imagine that if the same person takes different fMRIs, it's because it's the same person, you would expect that some information should be the same across layers. Okay, so when L equals 1, the model is just the random dot product graph model introduced in 2007 by Young and Hernan. And then the model that we wrote is very, very similar, almost the same as these papers, Arroyo 2021 and this one 2020. And there are other alternatives in the literature that have some modeling of tensor data as well. Okay, so how do we estimate the tensor P? So how do we estimate these probabilities of success? So to estimate the tensor P, we use inspiration from this algorithm based on the matrix low rank decomposition. So basically, what we do is that for every dimension S of the tensor, we take the matrixation of the tensor. And this is a matrix. And so we think of this matrix as being low rank. So then what we're going to do is that we're going to estimate a low rank representation of that matrix. And we do that with this algorithm that is called heterogeneous PCA. Basically, heterogeneous PCA extracts a low rank structure of that matrix. So we take that low rank structure representation and we call it U hat S. And then we take all of them and project the data into this thing that captures the low rank representation along each dimension. And so mathematically, it is this product after applying the heterogeneous PCA along each dimension. This gives us the probabilities of success, and then the probabilities of success could be beyond 1 or below 0. So we then just normalize it. And that produces an estimate of P, the probabilities of success. Yes.
Sorry, if you go back to with the sharing of the, if you go to your previous,
Yes.
sorry, not this, right, that the X13,
Yeah.
you have sharing information across layers. Now you're doing this. The components that you're calculating in this way, are those the shared parts?
The components are basically, we find components along, when we do the matrixation along each dimension, we
Each
find
of it, not across layers.
we do that for each layer. So layer 1, we do a matrixation along the first dimension, and then we find the data is using all the layers at the same time. Okay. So when we do the matrixation along the first dimension, all the layers are used, and we find a representation of that. And then we do the second dimension, and then we do the third dimension, and then we project A onto that thing, and that's the final tensor that we get. And the heterogeneous PCA, basically what it does is just to find a lower rank representation. So you need to specify the rank R and then the matrix sigma. And basically it takes the matrix and it writes the singular value decomposition. And then it takes the first R components, the corresponding to the largest singular values. And then it does this iterative algorithm where the diagonal elements of the matrix are set to be 0. But essentially it's just a rank R representation of the matrix. And that's what we use along each dimension of the tensor before doing the projection. So that is the algorithm. So let me explain what we can say about this algorithm. There are two cases, the fixed latent position and the random latent position. So under some assumptions, the assumptions require something about x, basically that the singular values of x, and x, by the way, is the matrix that has these guys as the rows. So you put all the latent positions into a big matrix X. And if you do that, we just need some assumptions about the singular value decomposition of X and some assumptions about the matrix Q. The matrix Q has all the weight matrices. For the random latent positions, we also can make some general assumptions. Basically, if you generate one vector from the distribution for the random latent positions, you can look at the second moments of that latent vector, and then we require that the matrix of second moments is well behaved, basically. And here is what we can show. We can show that if you estimate p hat with the tensor heterogeneous PCA, and if the adjacency matrix is generated either from the fixed model or the latent position model with the appropriate choice of ranks, then with high probability, the tensor that you estimate is close to the tensor that you want to estimate, and the error rate is of this order, high probability. This is interesting because a lot of people have tried to estimate low-rank tensors. And in the previous works, they all have upper bounds, but the upper bound that we find for estimating P is actually the sharpest upper bound for estimating a tensor. It's the sharpest upper bound in the literature when we compare it with the competitors. Okay, so now let me talk about the dynamic setting. So for the dynamic setting, the motivation is this. So you go, right, you take the fMRI, and the different regions of the brain represent the nodes, and you do this over, let's say, 12 minutes, right? Then you can create a window, a sliding window. Within each window, you can create a network of a binary network representing different regions of the brain. If they are firing up roughly at the same time, then that gives you a sequence of networks. But you can do this for different layers. So one layer is just resting case. The second layer is answering questions. So that gives rise to a dynamic tensor. In the airline example that I was mentioning, in that example here, we can observe each of these networks every day, right? So today we get one network for Lufthansa, one for Air France, one from British Airways. Tomorrow we might get a different network. The next day, a different network. So we get multi-layer networks at different time points. So we get a dynamic model. And that is very natural, based on in examples like the ones I described. So then what do we do in the dynamic case? So in the dynamic case, basically we have a random tensor that now depends on the time t. And we assume that in the fixed case, it follows a multi-layer random dot product graph with fixed latent positions. And we assume that the weight matrices are allowed to change, but the latent positions are the same. So the latent positions stay the same throughout time, but there could be changes in the way that the latents, the weight matrices change. So that's our assumption for the latent, for the dynamic model. And so we want to do online change point detection. So in online change point detection, basically we're collecting the data sequentially. Every time t, we get a new tensor. And the goal is to raise an alarm the first time that something is out of order. So you collect data and then you want to raise an alarm as soon as possible once we detect that there is a shift in the distribution of the data. So in this online setting, then there are two examples, two cases. The no change point and the one change point. In the no change point, the assumption would be that the weight matrices are actually the same across time. They do not change. In the one change point case, the assumption will be that there would be some time delta where the latent position, the weight matrices have changed. So imagine in the case of networks, in the case of airlines, right? So before COVID, you had British Airways, Air France, they have dynamic models. Let's say you have dynamic models for those networks. And then COVID hits, right? Before COVID, maybe everything was the same, but after COVID, now the way that British Airlines operates or Air France operates is different, right? Now their weight matrices are different in our model. So that is how we capture the change point case. And so what do we do in change point detection? So in change point detection, we want to have an algorithm that will raise an alarm as soon as possible, but we also want to have a type 1 error control. And so the type of control is like this. So we're going to have an estimator delta hat of the change point, but we would like to have a tolerance against mistakes. So we choose alpha in 0, 1, and we control the probability of raising a false alarm. We want that the probability that we will raise a false alarm, we want that to be small. At the same time, though, we want the difference between the estimated change point and the true change point, which is known as the delay. We want that thing to be small. So we want to have a control the type 1 error while having a quick detection of the change. So that is what we want. So what we do is the following. Basically, what we do is to have an algorithm where the collection starts at 1, and then we have t. Let's say that we are at this point t. So then we look at s, time s. And so what we want is to see what is the evidence that s is a change point between 1 and t, between the data that we have seen so far. How good of a change point is the point s? So to do that, we would like to have a discrepancy measure that compares the data between 1 and s and the data between s plus 1 and t. And we call that discrepancy measure d hat st. It measures how good of a change point is s between 1 and t. And so the idea is that if this thing is greater than or equal to a threshold, then we're going to stop and say, oh, there is a change. And we do that for every s between 1 and t. And then we do the same at t plus 1. And every time a new point comes, we do the same. So then really the only thing that we need to is to say, how do we construct the discrepancy measure? The formalization of what I just said is this algorithm. But how do we choose a discrepancy measure is very naively done by estimating the tensor from beginning to time s. So from beginning to time s, we estimate the probability tensor, and we call that p hat 0s. And then from s to t, we estimate the tensor as well, but only using the data between s and t. And then we take the Frobenius norm of the two. If the Frobenius norm is large, then we raise an alarm and we stop. If it's below the threshold, then we keep collecting data. So that is the detection algorithm for fixed latent positions. There are some assumptions that we can make, and here is the theorem. Basically, under some choices of tuning parameters, we can guarantee that the online detection algorithm will have a desired type 1 error control, but also with high probability, we're going to raise an alarm between the change point and the change point plus something. So we have a guarantee that within a range after the change point, within a frame of time, we will raise an alarm with high probability if there is a change point. And if there is no change point, we will just not raise an alarm with high probability. So that is what we can say for the algorithm. Now, let me say what can we do in the dynamic case, and why does it matter? So the idea is this. So in the fixed latent positions case, we have t equals 1, t equals 2, and our nodes could be Oscar, Bob, Alice. These are our nodes. Oscar, Bob, and Alice. These are the nodes at time t1 and t2. So in the fixed positions case, each of these names gets an xi, and the xi's are the same across T. Now, in the random case, in some applications, the labels in time T1 and T2 don't need to be the same. For example, if you look at a network like Twitter, or now X, the people who are on X today are not necessarily identical to the people on X tomorrow. Or another example, maybe today we look at how people are connected, but we use TikTok to see that their connection. Tomorrow we might choose a different way. For example, we might look at Instagram. So when the nodes don't have label, so if the nodes don't have label, it doesn't make sense to talk about the same xi across T because there are no labels. So in that case, we would have, let's say, our nodes are Oscar, Alice, but then at the next time, they are Bob and John, and each of them would have a latent position, but there is no sharing of information between the latent positions because there is no labeling. That is known as we don't have vertex correspondence. So that is the case when we don't have nodes labels. And so what we do in that case is we model with a dynamic model like this, but now at every T, we draw new latent positions because there is no information sharing across T. So that is the difference between fixed and random latent positions. The random latent position makes sense when we don't have labels. The fixed latent positions make sense when we have nodes that are shared across T. Okay, so then how do we do change point detection here? To do change point detection here, we need to detect how the layers change across time. And so again, there will be two settings in this case, the no change setting and the one change point setting. In the no change point setting, the distributions from which the latent positions are drawn, they stay the same. The weights also stay the same. So it's basically at every time T, we have the same distribution and we are randomly generating nodes and then observing a tensor, and that is happening across time. But the latent positions are drawn from the same distribution and the weights are the same across T for every layer. That is the no change point case. In the one change point case, what we do is we define what it means to have a change. And what it means to have a change is the following. We look at what is the probability that node 1 and node 2 are connected in the first layer? This one conditioning on X, on the latent positions at time 1. This is a random variable. Conditioning on the latent positions at random 1, this probability is a random variable. But we can also look at the random variable that represents the probability that they are connected, 1 and 2, but in the second layer. And conditioning on the latent positions of that time, that is also a random variable. And we can do that for every layer. So that defines this latent random variable that depends on the weight matrices and depends on the random objects. And we just ask, is there a change in the distribution of this latent thing? And what we're going to do is try to have an estimator for quantifying if there is a change between the distribution of that latent thing at one time versus the next one. So in order to do that, we do the following. So we need some assumptions, but I will not go over the assumptions. But we do it in the following way. So basically, our space of nodes is very large. Oh, sorry, of edges is very large. It's like this. So these are all potential edges that we could have. Now, this space of edges is very complicated because the data that we see for each edge, whether or not we observe the connection, those data are not independent. So this one is, the data for this one is going to be dependent with the data for this one because they share the same node 1. The data for this one is going to be same as this one because dependent to this one because they share node 2. Whenever two edges share the same node, their data are not independent in our model. So in order to have an estimator that we can study, we do a partitioning of the edges. So the partitioning will do something like this. And it is done in a way that the data within each partition element are going to be independent. And this is just for technical reasons. So that is this definition here. And so then what we do is the following. Okay, we wanted to estimate a change in distribution between the latent objects. So what we do is a kernel test. So the kernel test is going to be based on, we look at the data from 0 to S, the data from S to T, and we measure their discrepancy by taking a difference of K evaluated at this, where K is a kernel. So we estimate the latent positions, and then we took a kernel difference between them. We passed them through a kernel and compared them. But then we average across all these blocks that I was talking about. And the average across the blocks incorporates a weight that depends on each block and the sum of the sizes of the blocks, and then we need a bandwidth. So we do that to construct the discrepancy measure, but then this needs to have an estimator of the tensor between any two fixed points, between 0 and S. How do we estimate the mean? And to do that, we are free to do whatever we want. So we take the average, the running average between S and T, and then we do denoising of that running average. And that is what we input in the kernel difference. Now, for the average here, one issue that we get is that even though each matrix AT has a tensor probability PT, and these guys are low rank, when you take the average of these matrices, the mean of the average is not necessarily low rank. So if you have a bunch of low rank matrices or tensors, and you average them, the mean the mean of that does not need to be low rank. And so that is a difficulty that we need to face. Even though these were low rank, the average doesn't have a low rank structure. And here we can specify any methods for denoising. So the method that we use is very similar to the previous one in the static case. But now what we do is we take the matrixation of A along each dimension. And instead of keeping the R singular values from that decomposition, we only keep the largest singular value. And we throw away all the others, and then we project A in the same way, and then we do the scaling. The reason why we only keep the largest singular value is because the average of these guys is no low rank, and if we keep more singular values, it turns out that it's just adding noise. It's just adding noise that is increasing in variance, and it makes the estimation worse. And we notice that empirically and theoretically. So we only keep the largest one. And that is basically what I just said. So this guy is no longer low rank, and so we only keep the largest singular value of that. Anyway, so for this random latent position case, we can show that under some choices of tuning parameters, with the probability that we raise a false alarm is less than or equal to alpha when there is no change point. But when there is a change point, the probability that we see an alarm between the change and the change plus this, that is a high probability. So we guarantee that type 1 error control, and we will detect the change point within a reasonable amount of time. And reasonable meaning that this depends on n and the size of the change, and then other parameters that are small. The number of layers is usually small, dimension is usually small. This is a logarithmic factor in the numerator, and here we have n in the denominator. So if we have a lot of nodes, quickly we can detect the change point. Okay, so now I am going to talk about a real data example. The paper actually has a lot of simulations, and for reasons of time, I will not go over that. So in the simulations, I will focus on the random latent positions case. Sorry, for the real data example here. And to do this, I should say that our algorithm is the first one to do change point detection with tensor data. And so how do we compare with other methods? So what we did is we look at other methods like this one, and a KNN based methods. Each of these methods can estimate a low rank tensor. So if you give them a tensor, it can estimate a low rank tensor. How do we go from there to change point detection? well, we can do the same algorithm that we do, and instead of using our way of denoising, this was our way of denoising, we can just replace with other ways of denoising based on the existing works, and keeping our algorithm the same everywhere else. That means that as long as you have a way of estimating a low-rank tensor, you immediately get a way to do online change point detection if you just follow this algorithm. So in that way, we can evaluate the quality of our denoising algorithm and compare it with others in the context of change point detection. And so that gives rise to a bunch of competitors, but I should say these were not original methods for change point detection. They were for tensor estimation only. Okay, so, I guess I do have simulations here. So I gave this talk the other day, so I am confused as to which version I am given today. So anyway, so for the simulation, let n be the number of Monte Carlo trials. So, and then we are going to estimate the change point with as t hat, u, where u is the trial. And then we're going to have a time horizon. So we're going to start from 1 all the way to uppercase T. And there are 3 different metrics of interest. One is the delay. The delay means that this is an indicator. So this is indicator of the set. So in the denominator, we have the number of trials for which the change was detected after the change point. So this is out of the trials, how many times we detected the change after there was a change in bit. But it could also happen that we didn't detect the change, and it just happened that we kept collecting data and we never raised the alarm. So that is included here. So that delay would be the fraction, the fraction of all of those, sorry, the average across all of those between the distance of the estimated change and the true change point. So out of the times that we detected the change, what is the average of the delay? So that is what we call delay. Another metric of interest is the probability of false alarm. And this one is, out of all the trials that we have, what is the proportion of times that, unfortunately, we detected an alarm before the true change? So the proportion of times that we say, oh, there is an alarm here, even though the change point didn't happen yet. So it's the proportion of false alarms. Another one is the proportion of false negatives. And this is the time that we went beyond the change point, but we just never raised the alarm. So we would like to keep all of these things small, right? Smaller the better for any method. And so there are a lot of tuning parameters to choose. So we have some guidelines for our tuning parameters. Essentially, for any online change point detection method, what people do is basically the following. So you usually have some preliminary data, and you know that this data didn't come from the change point model. So for example, if you're talking about the COVID case, this would be data from before COVID, and we knew that the airlines were not making changes during that period. Or in the case of brain, this could be just a person taking an fMRI in the resting scenario where they're just laying there. So this is the case with no change point. And so what we do is that we have some time series of data like this, and then we do permutations of this time series. Every time that we do a permutation, we rerun the algorithm pretending that our data is the permuted data. And that gives us a list of statistics, and then we calibrate the threshold so that the proportion of false alarms is very small. So we can do this in general for any method, and that is what we do to calibrate the tuning parameters. Yes.
So you have time point 1, time point t,
yeah,
and you're going along this with s as a scale, right?
Yes.
But is your sort of the parameters there that you're tuning, are they the same?
They're the same.
In terms of what you're comparing? Because if you have small data at the beginning,
yes,
and large at the end, then you're
yes,
more likely to have a false positive.
That's a great question. So are the parameters the same across T? So basically what we have is, we have a rule, T hat TST, and this is tested. Is S a change between 1 and T? And this one has some mathematical expression that depends on S and T. And this expression involves some constant and some tuning parameter. So the way we compare is different, but there are some shared parameters across, and those are the ones that we are calibrating. But as you said, if you keep going and going, you probably need to adjust. So that is done with some mathematical expression here. Okay? Okay. Okay, so here is one scenario from the paper. The paper has many scenarios. In this scenario, we create the weight matrices, and they are WL across all the trials. And the latent positions are identically and independently distributed from a Dirichlet like this. So actually, we are randomly generating these latent positions from some Dirichlet distribution. That is before the change point. After the change point, what we change is the way that we generate the latent positions. Now they are generated from a different Dirichlet. And we want to detect, we want to see how the algorithms perform for detecting the change. The probabilities of links are given by this inner product with the weight matrix in between. So we try our algorithm, which is this, and then this algorithm is our change point detection algorithm with a competitor way, with the original way of doing denoising. This is the way that I proposed at the beginning, when you do the singular value in decomposition and you keep R singular values. This one is the one based on only keeping the largest. This one is based on a different way of denoising, and so on. And so what we typically say is that across the three metrics, when they are all calibrated in the same way, what we see is that our algorithm outperforms the competitors. For example, here, this is the delay. This is our delay. These two have this delay. And this one has a very high delay. And this one is the only algorithm in the literature that we could have used from before our paper. So it was the only existing algorithm. And you can see that it performs very poorly. The reason is that this KNN does not use any information about the network structure that we are doing. This is a generic algorithm for metric spaces. So our algorithm does really well. Okay, so finally, for the real data, I go back to the transportation network, in this case, US Air Transportation Network data. And this is available at the Bureau of Transportation and Statistics. And what we have is, we look at these airlines, Southwest, SkyWest, United, and Delta. These are going to be layers. So each airline is a layer. And then we look at different numbers of airports, 50 or 75, to just look at the sensitivity of the result. The airports that we choose are the largest airports in the US, and or the busiest airports. And we look at 91 months or T instances. And this is the data from 2015 to 2017 is used. This one is used for calibration. So from 2015 to 17 is the original data that we use to calibrate all the tuning parameters. And then after that, we are just going to detect a change from 2015 to 22. Okay, so now in this case, this is a case where the nodes actually have label, right? The labels of the nodes would be LAX, JFK, LaGuardia, the Burbank Airport, and so on. So the nodes are actually the same. So we did both experiments to see if we can detect the COVID change. One experiment is just to use the label information. And the one I'm presenting here is we just throw away. We just pretend that we don't know the names of the airports, and we don't know that they are the same across T. And so we do that, and with this choice of alpha for the type 1 error probability, we compare all the different algorithms. And what happens is that our algorithm detects a change point in 2020, in May of 2020, which aligns with COVID, and the other algorithms, they do as well. So these are the algorithms based on our online change point detection method, but replacing denoising with their version of denoising. So to be fair, those were not algorithms that existed in the literature, but we made them by just adapting their procedure for estimation, adapting it to the change point case. So they all detect the COVID change. And then KNN, the only method that was available in the literature before, it fails to detect the COVID change. So that will be this real data example. I am currently working on an example on an application with the brain data, but that is under development. Yeah, so there is just more information, and the paper is in archive. And so if you just Google the name of the talk, then you can find the paper. And thank you for your time. I can answer questions now. I do apologize. The annotation is very heavy, but I am hoping that at least the high-level ideas are understandable.
Do we have any questions? Comments?
Yes.
Just for understanding, so using the last example you present, so here the data summarize average across the whole month. So in your model, if I kind of have a higher time resolution, say I summarize data every 2 weeks or every week, well, that helps us like detecting the change point.
So so what happens is if you use bigger windows, right? So in the airport case, you can do week, you can do every few days, or you can just do every day. In the case of brain data, you can take different time windows, right, to construct the network. Because basically for each region, you get a big vector every I forgot how often, but you get a big vector, and then you calculate the correlation between those vectors, and that produces a network. But you can use different resolutions, right? So that's up to the practitioner what resolution they would use. So if you use, let's say, higher resolution, more resolution or longer periods of time to construct your network, then you have more information. So that means that you will detect changes quicker. But that also means that quicker in the sense of those big windows that you are setting. So it's like a trade-off. To know which way is the best, I don't know. I mean, that depends on the type of data that you have. Yeah.
So the number of time points, increasing the number, for example, if like, say we have a patient and like we recommend have annually like physician exam, but if the patient has some history, we want to increase the number of like exam time. But if we assume the underlying process is kind of a slow process, but we want to detect if there's set of disease, then like increasing the time point, like increasing the frequency.
It would help because you would have more signal, more data. Yeah.
More data, like is that representing your?
In the theory, yes. Yes, you would have more data and then you can detect quicker, yes.
But for airport example you showed, it like.
I don't remember the reason. There was no real reason why they used that. That was just an example, yeah.
Oh, okay.
But for example, another data that I used before was like brain data like this.
Just to remind you, there's a class that starts in 1 minute.
Yeah.
And it didn't matter. Yeah.
I do one quick question.
Yeah.
So this is all assuming sort of over time.
Yeah.
What if it's so like the fMRI data, this is you're looking at experiments, experiment A, experiment B, experiment C. So there's no natural time. What you're trying to do is say, is the network from this experiment different than all the others?
So you can try to do one naive way that you can do is like a testing.
Yeah.
So I do have another paper where we do network testing, and you don't even need